Hi everyone, welcome back to the channel. So in this video lecture we'll be solving this problem, second minimum time to reach destination, which is a Leetcode hard problem. So in this problem we're given a city represented as a bidirectional connected graph. It has n vertices where each vertex is labeled from 1 to n. The edges in the graph are represented as 2D array edges, where each element in the edges array is basically a pair representing a typical edge between those pair of vertices. So it denotes a bidirectional edge, so there is a vertex between ui and vi for the pair ui vi. Every vertex pair is connected by at most one edge. That means there are no multiple edges and also there are no self edges. The time taken to traverse any edge is same, that is time minutes. Now each vertex of the given city has a traffic signal which changes its color from green to red and vice versa after every change minutes. So it periodically changes, or the color flip periodically. It starts from green. Initially when we are starting, all the lights are turned green and all of them change at the same time. So we can enter a vertex at any time, but we can leave the vertex only when the signal is green. We cannot wait at a vertex. If the signal is green, we have to move out of it. What we have to do in this problem is to find the second minimum value, which is defined as the smallest value strictly larger than the minimum value. So let's say for instance we have an array 2 3 4, then the minimum value is 2 and the second minimum value is 3. Similarly, another array we have 2 2 4, the minimum value is 2 and the second minimum value is 4. So we are given n nodes, edges array, time and change. We have to return this second minimum time that it will take to move from vertex 1 to vertex n. So there are two node points which we have to keep track. The first one is that you can go through any vertex any number of times, including 1 and n. Fine. And we can assume that when the journey starts, all signals have just turned green. So initially all of them are green. So let's better understand the problem statement using an example. So here we have an example, and the time it takes to traverse any edge of this graph is 3 minutes here, while the traffic lights chain flips after every 5 minutes. So initially we are standing on vertex number 1, we want to reach the vertex number 5. So let's check out the possible paths that we can have. So one of the way to move from 1 to 3 would be to move from 1 to 3, consuming 3 minutes, then from 3 to 4, consuming yet another 3 minutes, finally from 4 to 5, consuming yet another 3 minutes, which will give me 3 plus 3. And here I can see that while I'm traversing this edge 3 to 4, at some point the lights will be flipped. That means initially they were green, they will be flipped to red. Fine. So after 3 plus 2, so this is 2. After 5 minutes, the lights will be flipped to red. So they are red at this point. And now I take one more minute to reach vertex number 4. Then on vertex number 4, I have to wait 4 minutes for the lights to turn back to green so that I can move out of it. That means I have to wait 4 minutes on this vertex, plus finally I move from 4 to 5, consuming yet another 3 minutes, finally giving me 3 plus 3 6 plus 4 10 plus 3 13 minutes. This is one of the paths. I have reached the destination 5. Let's take another path. Another path would be to move from 1 to 4, consuming 3 minutes, then from 4 to 5, consuming yet another 3 minutes. That is 3 plus 3, 6 minutes. And that's all. These are the possible two paths that we have. We don't have any third way to reach destination node starting from the node number 1. So this is the minimum cost or minimum time if we move from 1 to 5 through node number 4, and this is the second minimum time if we move from 1 to 4 through node number 3 and 4. So what do we want in this problem is that the second minimum time to reach the destination node starting from the source node 1. Hence 13 is my answer for this particular test case. So how would I solve this problem? What is the intuition? What is the logic behind it? Let's see that. So let's see, there are few observations in this problem. So for this typical, so we have this graph and we start from node number 1. We want to reach node number 5. These are the parameters that I have. I have 5 vertices, I have 3 minutes, and I have flip interval as 5 units. So let's observe a few things. One of the thing is that we are starting from node number 1. So this is my source node and I want to reach this target node, and the graph is weighted. The graph, the edges are having the same weight. So it is, and we want to find the shortest path somehow. So this gives me a intuition of using shortest path algorithm, single source shortest path algorithms like Dijkstra algorithm. Can I use BFS here? Yes, because all the edges of the graph have the same weight, that is 3 minutes. So I can also use BFS search here. But we can't use standard Dijkstra or standard BFS to solve this problem, because there are certain constraints which are given in this problem statement. One of the constraints is that we don't want the shortest path or the path which consumes the minimum time, but the path which consumes the second minimum time. We want the second shortest path in the graph. Similarly, there is another constraint, that is after every 5 minutes the lights flips their color. So if they were green, after 5 minutes they turn to red, then after 5 minutes they turn back to green, and so on. So we have to handle that constraint as well. And okay, we can't move out of a vertex until it is green. We can only move out of a vertex if the lights are turned green. Otherwise we have to wait on that vertex for the lights to turn to green. So we have to handle that constraint as well. So how would we do that? Obviously we have to modify our standard Dijkstra algorithm a little bit. So let's see how to do that. So before we jump to the final solution, I'm assuming at this point that you know how the Dijkstra algorithm works, because I will be solving this problem using that algorithm. So what do we do in Dijkstra algorithm? Basically we have a source node and we have a destination node. We push that source node into a priority queue because we use that priority queue, and in the priority queue we keep the nodes sorted according to their distances from the source node. So in Dijkstra algorithm we basically take a priority queue and they are sorted in increasing order of the distance from the source node. So at any point we pick the node from the priority queue which has the shortest distance from the source, and using that node I perform the relaxations to the adjacent nodes of the node which I have picked out of the priority queue. So let's say I have node number 3 into my priority queue, which is the closest node to the source node. Then I will pop this node out of the priority queue and I will update the distance of node number 4, which is the adjacent node of the node number 3, using the shortest distance of node number 3. So let's say the shortest distance till node number 3 is s units. Then to perform the relaxation over node number 4, all I have to do is to just put s plus the edge weight w. That is, I'm already assuming that if I am picking a node out of the priority queue, it has the shortest distance. So we have already calculated the shortest distance till node number 3, and now I'm calculating the shortest distance till node number 4 using the shortest distance of node number 3. That's called relaxation. And if after I calculated the shortest distance till node number 4, I'm gonna push this node into the priority queue along with its distance from the source node, so that the same step can be performed for the adjacent nodes of node number 4, that is 5. So in this fashion, I will calculate the shortest distance till each node of the graph from the source node 1. So that's the working of Dijkstra algorithm. Let's see how we can modify my Dijkstra algorithm to solve our problem. So we know that in Dijkstra algorithm we take a distance array. So what is the functionality of this distance array? This distance array basically has a size same as the number of nodes, and we store the shortest distance into this distance array. Okay, so this is the typical distance array for Dijkstra algorithm. For each node of this distance array, I'm going to store the shortest path, shortest distance, or the minimum time to reach that node. So if the edge weight is 3 units, then to reach the node number 3, the minimum time would be 3. And we also use a priority queue. So this is basically a min heap. So in this min heap, we initially push the source node, that is node number 1, along with its distance. So 1 is pushed with the distance. The distance of the node number 1 is 0 because this is the source node itself. In this fashion, whenever I perform the relaxation on any node of the graph, I'm going to push it into the priority queue. And the nodes in the priority queue are sorted according to the distance. Fine. Then, so for node number 1, the distance is 0. So to solve this problem, since I want to find the second minimum distance or second minimum time, also have to keep track of the second minimum distance. So how would I do that? So let's say, so to do so, let's say I calculate the distance till node number 5 as 3 plus 3 plus 4 plus 3, that is 13 units. So I calculate it as 13 units. So till node number 5 I have 13 units. Or let's take a simpler example. So let's say I calculate the distance till node number 4 as 3 plus 3 as 6 minutes. I move from 1 to 3, then from 3 to 4. And till now this is the shortest distance. So I store 6 in my distance array. That is, I perform the relaxation over node number 4 through node number 3. Okay, so let's understand this using this example. So let's say initially I push node number 1 into my priority queue. Then I run my Dijkstra algorithm, and when I run the Dijkstra algorithm, I pop this node out of the priority queue, node number 1, and using this node number 1, the shortest distance till node number 1 is 0. I perform relaxation over its adjacent nodes, that is 2, 4 and 3. So for 2, the shortest distance that I get is 3 because I just have to traverse this edge. Similarly for node number 4, the shortest distance is 3. Similarly for node number 3, the shortest distance is 3. And I push these 3 nodes into the priority queue. While pushing these nodes into the priority queue, while also updating their distances into this distance array. So this distance array will be updated like for node number 2 I will have 3, for node number 3 I will have 3, as well as for node number 4 I will have 3. Then they are into the priority queue and they are sorted according to their distances. Since the distances are same, I can choose any vertex from the from the priority queue. Let's say node number 3 is present at the top of the priority queue, so I pop node number 3. So when I pop node number 3, that means I have already calculated the shortest distance till node number 3. Now I will perform the relaxations over the adjacent nodes of node number 3. So the adjacent nodes of node number 3 is the node number 4. So I traverse node number 4 and I see that the distance till node number 4 when I pass through node number 3 would be 3 plus 3, that is 6. But in the distance 1 array, I already have its distance as 3. So 6 is worse than 3. So I can't update this distance for node number 4. But I will take another array. Let's call it distance 2. This array is initialized to a very large number and I will put 6 here. And since I'm updating my distance array, I'm performing relaxation, I'll have to push this node into the priority queue second time. So I'm pushing node number 4 into my priority queue a second time. Fine. So notice one point, if I performing two relaxations for a particular node, that is, in first time I calculated the shortest distance through node number 4, second time I'll calculate the shortest distance through node number 3 for node number 4. So I have to perform relaxations two times, and hence I'm pushing this node two times. So that's the trick. When I pop this node out of the priority queue twice, so I'm popping this node twice out of the priority queue because it was pushed twice. That means I have calculated my second minimum distance. That's the trick. So I will return the second minimum distance right from that point. Now, how can I ensure that the second time when I push this node will always give me the second minimum distance? How can I ensure it? The observation is simple for that. The graph is weighted, but all the edges has same weight. What does that mean? That means, let's say instead of this graph, the graph is, let's say, like this: 2, then I have another node 6, then this 6 is connected to node number 4. Let's say the graph is like this. If the graph is like this, then first of all I will push node number 4 when I'm starting here, when I'm traversing the adjacent node of node number 1. Second time I will push the node number 4 will be when I will be traversing the adjacent nodes of node number 3, not the adjacent nodes of node number 6, because this is present at next level. So this is, let's say, level number 1, then this is level number 2, this is at level number 3. So I will traverse the adjacent nodes of node number 3 before I traverse the adjacent nodes of node number 6, because this is present at the top of the priority queue. So I will push node number 4 twice while I traverse the adjacent node of node number 3. Hence, I'm already sure that when I'm pushing this node second time, I'm calculating the second minimum distance. So that's the trick. I hope you got the idea what I'm trying to do here. Rest everything is Dijkstra algorithm. We just have to handle these two arrays. We just have to check when to update distance 1 and when to update distance 2. Fine. Now let's jump to the, so let's see how we can handle the condition of lights flipping. So so imagine this scenario. We have this graph initially at time 0. C basically represents the change, and the change is basically the interval after which the lights flip. So initially from 0 to C, the lights stays green. After we have covered the interval C, from C to 2C, the lights will stay red. Then from 2C to 3C, the lights will stay green. And finally, from 3C to 4C, the lights will again stay red. So if I list out the intervals for green area, or for green intervals, then they would be 0C, 2C, 3C, and finally 4C, 5C. In a general sense, what I can write, 2 multiplied by C multiplied by M to 2 multiplied by C multiplied by M plus C. Fine. So M is basically a typical integer. Initially M is 0. So when M is 0, this will be 0 and this will be C. When M becomes 1, this will be 2C and this will be 3C. So I am basically listing out my green intervals. So this is the general form for green intervals. So how would I check if at any particular time the intervals are green? So let's say I'm traversing this graph and the edge weight for this graph is 3 units or 3 minutes. So 3 plus 3, it would be 6 when I reach node number 4. So how would I check when the time is 6 units, the lights are green or red? How would I check it? I just have to check whether this 6 lies in this type of interval or not. For that, I will divide my 6 by the change which I have, and the change is 5, because let's say after every 5 minutes the lights change. So what this gives me, basically this gives me the number of flips that I have covered till now. So in 6 minutes I would have 6 divided by 5 flips, that is 1 in this case. That means after one flip, and after one flip I can see that the lights are turned red. So if I have odd number of flips, so this is one flip, this is two flips. After even flips I have green lights, while after odd number of flips I have red lights. So when I have one flip, I will check if it is odd or even. So since it is odd, that means that lights are turned to red. So here I have lights turned to red. So that's how I am going to check for whether the lights are green or they are red. Since they are red, I have to wait for some time to move out of this vertex. Now the next question is, how much time do I have to wait? How would I calculate that? Simply calculate the number of flips till now. That is done by dividing the time by the time interval of the flips, that is 6 by 5, that means 1. So I have encountered exactly one flip till now, and since I have encountered one flip till now, I want to turn back. That means I need one more flip to turn back to green. So I need one more flip. So we will have exactly two flips before I move out of the current vertex. So in two flips, the time consumed that would be calculated by the interval size after which the flips occur. So that interval size is 5. So 5 divided by 2, that will give me 10. So I would take exactly 10 minutes before I move out of vertex number 4. Is it the correct answer? Yes, because 3 plus 3, 6, while I have to wait for 4 minutes in this vertex 4. That would give me 6 plus 4, that is 10. So that's how I calculate this value. Fine. And then to move to vertex number 5, I would consume yet another 3 minutes. So that would give me 13 units of time. That's how I calculate the waiting time at any particular vertex. So I just have to check if the flips are odd. Then I perform this computation. If the flips are even, in that case I don't have to wait. I just add the time to move to next vertex to the current time. Fine. So that's how the green and light constraints are handled. I hope you got the idea. If you have any doubt, please post it in the comments. I will try to answer the comments as soon as possible. So let's see the implementation. So this is the second minimum function, which takes in the number of nodes, the edges array, the time variable and change variable. I declare a adjacency list that is going to store the graph, and I build the graph from this edges array. So I create bidirectional edges, then I resize the distance 1 array and distance 2 arrays and initialize them with a very large value, and then I declare a priority queue or a min heap, and I initialize this min heap with the source vertex. The first integer is basically the distance from the source vertex. Then I initialize the distance 1 and distance 2 array for node number 1 as 0. Then I run my while loop. So in this while loop I pop the top node of the heap, that represents basically the node which has the shortest distance from the source node 1. Then I pop that node from the priority queue. And what I'm doing here, remember, we have to pop a node, or we have to pop a particular node from the priority queue exactly twice so as to calculate the second minimum time. So this frequency array is basically used to check for that. So if this is 2, that means I have popped this node out of the priority queue exactly twice, and hence the current distance that it has, or the time taken that we have stored for this node, is the second minimum time. So I return that second minimum time right from here. Otherwise I have to move to the adjacent node, so I find the waiting time here. So if the number of flips are odd, then I calculate the waiting time. How would I calculate that? That would be calculated by dividing the time taken till now by the change plus 1. So that will give me the total number of flips that I have to encounter before I move out of this vertex, and the time of flip for each, and the time interval of flip is change, so I multiply this change with that value. So this represents the number of flips, this represents the time taken in each flip. So this basically gives me the time that we have to stay till the current vertex node before I move to the adjacent node, and this time is basically the time which is added to the current time taken to move to the adjacent node. Otherwise, if the flips are even, I don't have to wait on the vertex, I just move out of the vertex and add the time to move to the adjacent node. So in this fashion I'm handling this condition of signal flips. Then I traverse over the adjacent nodes of the current node and I check if the frequency for any node is 2. That means I have already pushed this node twice in the priority queue, so I don't have to process it further. I just continue right from here. Otherwise, I'm checking if the time taken to reach the neighbor node is greater than the time taken that we have here. That means we have a scope of relaxation here. We can improve the time taken to reach this neighbor by replacing it with the time taken that we have here. So I update my distance 1 array, while the distance that I already have for this neighbor, that I will store into the distance 2 array, because let's say I update the time from 6 to 3. So if 3 is the minimum time, then 6 will obviously become the second minimum time. That's why I'm updating this distance 2 array, and I push this node into the min heap along with its time. So if this condition is not met, then I will check for the distance in distance number 2. So if the distance till neighbor in the distance 2 array is greater than the time taken that we have here, in that case we also have to handle one more condition, that is, I cannot have this time taken as the minimum time taken to reach the neighbor vertex, because if this is the case, then we can't have the same time to reach the particular node. That means we can't have the first minimum time and second minimum time to be same. They must be different. That's what I'm handling here. And hence I update my distance to array with this current value, and I push this neighbor again into the priority queue. So I'm pushing a particular node twice so as to calculate the second minimum time or second minimum distance to reach that particular node. Finally, if we do not encounter our source node twice, then that means there's exactly one path to reach the destination node, or there is not even one path. So this is a default case, and in that case I will return 0. So I'm returning 0 at the end of this function. So that's the implementation of the idea which we explained in this video lecture. Let's analyze the time and space complexity. The time complexity for this given implementation is the same as the time complexity of Dijkstra algorithm. That would be n plus e log n, where n represents the number of nodes and e represents the number of edges. While the space complexity is also same, that is n plus e, because I am using a min heap here or a priority queue. May have all the nodes in the worst case. So let's jump to the implementation part. Okay, so this is the solution class in which we have our second minimum time function, which takes in the number of nodes, edges array, time variable and change variable, and it returns the second minimum time to reach this destination node. So I declare a graph as adjacency list, which has size as n plus 1. Then I create my graph from the edges that I have been given from this edges array. So I create bidirectional edges. I declare a priority queue. So I declare a priority queue, and also I also declare two distance vectors. Distance 1 of size n plus 1 initialized to a very large number, and distance 2 of size n plus 1 initialized to very large number. Fine, then I push the source node into the min heap. So I push node number 1 along with its distance from node number 1, that would be 0. Then I run my while loop, and I pop the top node out of the queue. So I pop the top element from the queue. That would be, there would be two element, time taken and the node. So I will pop min heap dot top. I will pop this node out of this queue, and I also have to declare, I forgot to declare the frequency array. I also have to declare the frequency array of the same size n plus 1 initialized to 0. So this is going to count if I am, so this is going to check if I have popped a particular node twice or not. So here I am counting the frequency of the current node. Then I will check if the frequency is if the frequency becomes 2. That is the case when I have encountered this node second time, and hence I will check if this node is basically the destination node. If this is the destination node, then this is the distance which I require, or this is the time which I require. So I return the time taken right from here. Otherwise, I have to check for its adjacent nodes. So before I traverse its adjacent nodes, I will have to calculate the time taken, the final time taken, where I need to handle the time which I need to spend on this particular vertex because of the red lights. So for that, I will check if the number of flips that I have encountered till now, if the flips are odd, in that case I have to wait. So how much time do I have to wait? That would be given by this equation, change multiplied by time taken divided by change plus 1. And to move to adjacent vertex, I need to add time value. So this will give me the final time to move to adjacent node. And if I do not have to wait, then this time taken would simply be the time taken, the current time plus the time to move to adjacent node. Fine. So then I traverse the adjacent nodes or the neighbor nodes of this current node, and I will check if the distance for the neighbor node is basically greater than the time taken that I have. If this is the case, then I will update this distance array for this neighbor. But before I store the value of, before I perform this relaxation, I have to store the distance for this neighbor in distance2 array. And then I will perform the relaxation for distance1 array. and I will push this pair, that is time taken, and the current node, that is neighbor, into my min heap. Otherwise, I will check if this distance, if this condition holds for distance 2. So if this is greater than the time taken, and here I have to check that if both of the arrays for this particular neighbor do not store the same time. So I have to check this, if the distance in this distance 1 array for this neighbor node is not same as this time taken. Only in that case I will update the distance to array, because that will become the second minimum distance. And I will push this node into the priority queue. So time taken along with the neighbor node. So in this fashion I will process my nodes, and finally let's say I never encounter our destination node 2 times. In that case I do not have a second minimum path, or a path, or a even second path to reach the destination. In that case I will return 0 by default. So this is how I implement the solution. This is just the standard Dijkstra algorithm with a little modification. So this is the trick which I had to use to solve this problem. So there are few learnings for this problem. One of that is, whenever we have to find a shortest path from a source vertex to a certain node, just think about the single source shortest path algorithms like Dijkstra algorithm, BFS algorithm. And if the edges have the same weight or they are unweighted, try to think using BFS. So this problem can also be solved using BFS. So this is an exercise. Try to solve this problem using BFS. So eventually when we solve a lot of similar problems like this, so we have a collection of certain tricks which are repeatedly used in these problems. Fine, so in future I will try to cover those patterns. I will try to solve more problems of the same algorithms like Dijkstra algorithm, BFS algorithm, so that you people become aware of those certain tricks. So this is the implementation in C++. Let's see the implementation in other languages. This is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button. I'll also try to solve this problem using BFS approach in my next video.